K8BYP with a non-hobby video on matching networks, actually building a network and seeing the dumpster fire that ensued. How hard can it be? 3 components, right? 3 components, although it's a jumble of capacitors. There's several to make exact values. 2 Toco FM IF transformers rewound, and capacitors strung together to make the correct value. Tested on my uber accurate 4-place measuring system, accurate to an ants you know what. This network's intended for my vacuum tube amplifier. 3-400 will go 800 watts BEP, and I'm calculating values for a fixed output network, which I don't know that that's ever been done. It's essentially always a fixed or roller inductor and the air variable or vacuum variable capacitors. The air and vacuum variables have essentially no losses, but the inductors spew field everywhere, and they're terrible. So I plan to use toroids and good fixed value capacitors. But something is desperately wrong here. Input 1730 ohms from the plate, output 50 ohms to the load, 10.1 microhenry, 168 picofarad, 2.77 microhenry. This ain't rocket science, but it doesn't work. That circuit is essentially a transformer. From transformer theory, we know dividing 50 into 1730 and taking the square root gives 5.88 to 1. So 5.88 volts coming in at the left will result in 1 volt coming out at the right if the network is correct. No cheap equipment. No cheap equipment. There's $25,000 in the late 1980s sitting there. That was $1,000 on sale. This ain't hobby. I know what I'm doing, supposedly. Good equipment. I know how to operate the equipment. I can probably design the equipment. Yet the experiment fails. Well, welcome to real life. That's what happens in the real world. The test and measurement problem is that the scope is an extremely good scope, 500 megahertz input, BNC 50 ohms. That'll be absolutely flat R50 at 3.7 megahertz, 80 meters. The generator can have its resistance set anywhere from 10 ohms to 10,000. So by the principle of reciprocity, the network is hooked up backwards with the output. No, correction. It's connected correctly forward with the output to the scope, 50 ohms, taking the place of the antenna. And with the generator keyed in to have an output resistance of, if it will focus, 1730 ohms on the bottom, and 5.880 volts peak to peak. And that should result in a 1 volt peak to peak on senior scope, except this is a dumpster fire. Graticule illumination, high-end scope, 500 megahertz. We're operating at 3.7 megahertz, no losses, no errors. It's been calibrated, 0.2 volts per division, 0.2468, 0.84 volts peak to peak. Appending our diagram, 5.88 volts peak in, 0.84 out. Where'd the other 0.16 volts go on the output? That's a significant amount. It's not a huge amount, but it implies either the network is not designed correctly, and I can assure you it is because I went through Radio Engineer's Handbook. I designed it, I built it. It didn't work quite right. I took the values, I manually calculated the network. It came out to within an ohm. The values are correct, but calculations correct, math carefully checked, good high-end test equipment. It's got to be poor components, loss, leakage, something, who knows what. The little cans are Toco IF transformers, the kind using the 10.7 megahertz IF in FM receivers. They're made for RF. They shouldn't be terribly lossy. There will be a little. It's possible to have incorrect values for the components and get too high of a voltage on the output. But a marginally low voltage implies losses. that implies that energy is being lost inside. I was able to drive this network backwards by the principle of reciprocity. This network doesn't know or care which direction is which. I put the generator in R50 and I made a load. In fact, I made two loads. I made a 50 ohm, that's a 50 ohm high frequency termination, and 1730 ohms of just garden variety resistors, but they're okay for low frequency. But terminated the input in the 1730 load and drove the output backwards from the generator, and I found that I had to set the generator output to 29 ohms to get the correct voltage output. So you're free to think about what that means. That means something wrong, significantly wrong. I made the measurements on these super duper accurate measuring system I developed just for this kind of purpose. And you can see figures to 4 places. 1.256 volts is not playing around, folks. That's accurate. But I had measured the capacitors at 3.7 megahertz. Of course, that's the frequency that networks intended to operate at. But I used varying different frequencies, 1.9, 3.7, and 7.0. And here's what happened to the capacitive reactances. Or actually not the capacitive reactance. My test setup measures the magnitude of impedance, mag Z, which can include resistance and losses. 1.9 megahertz, 281. 3.7, 145. 7 megahertz, 77. Something is badly wrong. So where's the error coming from? Probably capacitors. Here's information on one of them's at 270 picofarad, 3.7 megahertz. LCR meter reads, very nice, 274, 4 picofarad high. That's 157 ohms capacitive reactance, right here. But the precision measuring system indicates 145 ohms. So that means that there is, with dissipative losses, probably some dissipation factor that's shunting and causing energy loss. Knowing the measured mag Z of 145, and since the mag is lower, it has to be a parallel combination. I go to this table of formulas from rfcafe.com. Very good, reliable site run by an engineer. And find the parallel RC network under the column for magnitude Z. Find a simple formula. Omega is 3.7 megahertz times 2 pi. And calculate that. And what pops out is that capacitor right there at 3.7 megahertz is that network. 274 picofarad is measured by the LCR meter, which is reasonably accurate. That calculates to shunted by 365 ohms of mostly dissipation losses. On the basis of taking the test magnitude impedances and converting them to capacitance, there's very little change from 160 meters up to 40 meters. But this shows that this capacitor is absolutely useless for any precision testing on this network, and will turn into a fireball in the amplifier because 365 ohms is much of the magnitude of the capacitive reactance, which is 157. It's about twice the value. But with 2 kV across that 365 ohms, that's 5.5 amp, and that capacitor will turn supernova on the way to exploding. But that capacitor is rated for 2 kV. 274K, 2 kV. There's a bag from Newark, 270 puff, 2 kV, S3N dielectric. Here's a data sheet from Vichy, big name company. S3N Class 1 dielectric, good dielectric. Dissipation factor, 0.2% maximum. That is very little. But, see, rated voltage 2 kV. If you scroll down the data sheet, we find the ugly fact that, yeah, it might be 0.2% dissipation factor, but they only test them up to 1 megahertz. These are not RF capacitors. Vertical axis dissipation factor percent, that's basically the percent of the capacitive reactance. And notice the 1 megahertz line down here, dark line, and notice the very interesting thing that at high temperatures, the dissipation of the capacitor goes way, way down to essentially nothing. But at 25 degrees C, room temperature, more or less, the dissipation factor is about 1%. What happened to this mythical 0.2%? Well, they're playing games, playing marketing games. And if you don't know what you're doing, the capacitor is going to explode. For a 270 picofarad capacitor that's 157 ohms reactive, 1% of that is 2 ohms. Not bad. But measurements show something different. Measurements I've made at RF frequency with high-end test equipment show that that capacitor is completely unsuitable for not only use in the amplifier, but even for testing. I have to throw another 20-some picofarad across the capacitor in that network to get it close, and that's not right. Capacitors are strange animals. Be very careful with them. They can do weird things. It's common to think of them as having a chance of self-resonant frequency, but that's a minor problem. That's easy to find. But these temperature things, considerations can do strange things, especially what I've found in soldering them. Soldering, putting heat inside the capacitor through the leads makes a huge change in its impedance. Because the heat's conducted in through the lead, causes the dielectric and everything to expand, lowers the capacitance, and it takes much longer for the heat to escape than it does to get in. So make sure when testing capacitors, use the correct temperature. And if they're in a circuit working, they're going to be higher temperature internally, and that'll change characteristics. So again, that's why they use air variables and vacuum variables in amplifiers, and high voltage tube amplifiers. And I will either have to get correct RF capacitors or drop back to using air or vacuum variables. But that's what this part of what this project is about, to investigate using modern capacitors that are far superior dielectrics in an application that used to be a $500 air variable. So KBYP did it.